Hello, geometry folks. Today we're going to be talking about interior and exterior angles in polygons, and this picture has a little preview of what an interior angle is and what an exterior angle is. Um, but we're going to be talking about polygons, area, all that stuff, perimeter, and so to start it all off, we're going to talk about angles inside and outside of shapes. So what you're going to need are your notebook, calculator, maybe, and a pen or a pencil. Okay, before we start anything new, we always talk about vocab so that we have a basic understanding of what we're talking about when we start a new topic. So we have some vocab that you probably already know. This is probably background knowledge that you've learned before in previous math classes. A concave shape or a concave polygon. Here's a picture of a concave polygon, and when we say concave, we're talking about if a line that contains the side of a polygon and also points inside to the interior part of the polygon. So in our picture, it would be like this line or angle and this angle, they go inside the interior part of our shape. We call it concave. You can see that it's caving in on itself. Conversely, a convex polygon is something that is defined as not concave. So a good picture would be like the vertices or the endpoints of all the points in that pentagon are pointing outwards and there's no part where it's caving in. And then a regular polygon is one that has all congruent sides and congruent angles. So it's equilateral and equiangular for every type of shape. So here we have a regular hexagon because it has 6 sides, so it has 6 equivalent sides or congruent sides. Okay, so in this picture that we have on the front of our foldable, you don't have to write this down, I'm just going to explain the visual of what's going on. We have this blue 5-sided figure, so a 5-sided figure is a pentagon, so we have this blue pentagon here, and in the red it's telling me that a 65-degree angle is an example of an interior angle, or one that lies on the inside of my shape. When we talk about an exterior angle, when we're talking about an angle that's being created on the outside of a shape, but it doesn't go all the way around. It actually just goes until this like line that we've extended from one of the sides of the shape. So if you were to basically take 180 degrees minus the interior angle, that would get us, sorry, I'll switch to black, this exterior angle, which is 115 degrees. So this is just a visual of what is going on when we talk about what an interior angle is and what an exterior angle is. So now we're actually going to have some formal definitions and some theorems or formulas for them. So the formal definition of an interior angle is an angle that exists inside a polygon or a shape. We're going to need to know how to find the sum of interior angles. So just like the sum of all the angles added together in a triangle are 180, we're going to have a formula now to find how many degrees are inside of a polygon, or one with many sides. So that formula is n minus 2, where n is the number of sides times 180 degrees. And we'll explain on the next slide why this is. And then something else we're going to need to know is what each interior angle of a regular polygon would be. So then it would obviously be the sum divided by how many sides there are, or how many angles there are. So remember that n is the number of sides. Okay, exterior angle, the formal definition is an angle between any side of a polygon and a line extended from the next side or the previous side. And just think back to that picture when we drew one. If we had like a triangle, the exterior angle would be something like this. Remember the exterior angle theorem for triangles in one of our first triangle units? That's an exterior angle. So that's the formal definition. Then the sum of the exterior angles is 360 degrees, nothing super hard to memorize there, just like a circle. And then each exterior angle of a regular polygon then would be 360 degrees divided by n. So make sure you get these formulas, if you will, written down in your foldable. So we're going to explain why the sum of an interior angles polygon was that formula n minus 2 all times 180. This is the why does that work? This is the explanation for it. So we have this little chart that you should have as a foldable for your notes. And in our first column, we have the names of all of these shapes. And then we have a picture of the shape. And then we're going to fill in the columns for the number of sides. And then I'll explain what the number of triangles mean and the total degree measure. So in our first shape that we know is a triangle, and we have 3 sides. And so obviously there's only one triangle within a triangle, and we know that the total for all the angles added together inside of a triangle is 180 degrees. So if I have a quadrilateral, that's a shape with 4 sides, when we're asking how many numbers or how many triangles fit in this shape, we're trying to cut the shape so that we can create triangles. So for a quadrilateral, I'm going to actually have 1, 2 triangles. So then my total degree measure is going to be 180 times 2, which would be 360 degrees. And then if we move on to a pentagon, pentagon has 5 sides, and in our picture, if we try to cut it into multiple triangles, there's one triangle, and now we're back to a 4-sided figure, and we can cut it again. So now we have 3 triangles that make up a pentagon, and if we take 3 times 180, we get back 540 degrees. So this would be the inside, the total degree measure for the inside of these shapes. Moving on to a hexagon that has 6 sides. So if we draw in the inside, we come up with 4 triangles. So then 4 times 180 would be 720 degrees. And then if we go to a heptagon has 7 sides. So if we start, here's 1 triangle, 2 triangles, 3 triangles, 4 triangles, and a 5th triangle. And so then 5 times 180 would be 900 degrees on the inside of a heptagon. Moving on to an octagon that has 8 sides, and I'm sure you can see the pattern here. We're going to end up with 1, 2, 3, 4, 5, 6 triangles that make up an octagon. So if we take 180 triangle degrees times 6, we get 1080 degrees. And then last but not least, we have a nonagon, which has 9 sides. So if we cut those into triangles, we're going to have 1, 2, 3, 4, 5, 6, 7 triangles that make up a nonagon. And then if we take 180 degrees times the 7 triangles that make it up, we're going to have an inside total degree measure of 1260 degrees. So this is the why this formula n minus 2 times 180 works. Because we're starting to see our number of sides minus 2 gets us to the number of triangles, times that by 180 degrees for the sum of a triangle on the inside, and that gets us the total interior angle sum for each polygon. So now we're going to go through 4 examples using these formulas. So example number 1 is saying, find the sum of the interior angles of a 30-gon convex polygon. So we're assuming that it's a regular convex polygon, so with 30 sides. So we're going to need the n minus 2 times 180 formula because it's the sum of the interior angles. So n here is 30, so we're going to say 30 minus 2 times 180. So 30 minus 2 is 28 times 180 is 5,000 40 degrees is the total or the sum of all the interior angles added together in a 30-gon convex polygon. Example number 2, we need to find the measure of an exterior angle of a regular convex decagon. So that would be 360 divided by, well, we have to figure out how many sides a decagon has, which would be 10 sides for a decagon. So we're taking 360 degrees for the exterior angle divided by 10 angles in a decagon would mean that we have 36 degrees for each exterior angle in a decagon. So 36 degrees. And our last two examples for today. So example number 3, if the measure of an interior angle of a regular polygon is 108 degrees, then how many sides does it have? We are told the measure of 1 when it says n, we're assuming 1 interior angle. So the equation that we're going to have to set up is 108 is equal to n minus 2 times 180 all over n, because it's for one individual interior angle, not the sum of all of them, just one of them. So now we're going to have to solve for n because we want to know how many sides it has. Well, in order to get a variable out of the denominator, I'm going to have to multiply both sides by n. So now I have 108. N is equal to n minus 2 times 180. Well, before I can combine like terms, I'm going to have to distribute this 180 to the n and the negative 2 in parentheses. So I'm going to get 108n is equal to 180n minus 2 times 180 is 360. Now I have an equation where I just get all of my variables on one side. So I'm gonna subtract 180 to get n on the left-hand side. So 108 minus 180 is a negative 72n, and we're left with a negative 360 on the right because these cancel. Then we have to divide by negative 72 on both sides, and we get n is equal to 360 divided by 72 would be 5. So this is actually a pentagon. So it has 5 sides. So n is 5. Example number 4. Find the measure of the interior and exterior angles of an 18-gon convex polygon. So for an interior angle, we're going to have to use the n minus 2 times 180 all over n. So we're going to have 18 minus 2 times 180 all over 18. So 18 minus 2 is 16 times 180 all over 18. 16 times 180 is 2,880 divided by 18. And 2,880 divided by 18 is 160 degrees for an interior angle. If I want to do an exterior angle, I just need to take 360 divided by the number of sides. In this case, it'd be 18. And 360 divided by 18 is just 20 degrees. So an exterior angle measures 20 degrees in an 18-gon, and an interior angle measures 160 degrees in an 18-gon. So thank you all for taking such good notes, and I will see you soon.